All of you, welcome to this YouTube channel. In this video, we're going to discuss about thermal analysis of a composite modular wall, which is as shown in the given figure. Here, the outside of the composite wall is steel with the thermal conductivity of 20 watt per meter Kelvin. The insulating metal has the thermal conductivity of 0.1 watt per meter Kelvin. The bulk temperature on the left side of the wall is 220 Kelvin and the film coefficient is 200 watt per meter square Kelvin. On the right side of the bulk temperature is 300 Kelvin and the film coefficient is 20 watt per meter square Kelvin. In the main menu, select preference, select thermal, click OK. Next step is select preprocessor, element type, add element, select add, select solid, quad 8 node 77 and click OK and close this. Minimize the element type. Next step is metal properties, temperature unit. So here all the units are given in this problem as Kelvin, so keep the temperature unit as Kelvin, click OK. Next step is metal properties, thermal, conductivity, isotropic. Here the two materials are given. Here for the steel material the thermal conductivity is 20 watt per meter Kelvin. Click OK. And for insulator material we have to assign a metal properties, select materials, select new model, metal ID is 2, then click OK. Thermal, conductivity, isotropic. For the insulator material the thermal conductivity is 0.1 watt per meter Kelvin and click OK and then close this and minimize the metal properties. Next step is to creating a model. Modeling, create, areas, rectangle, bidimension. Here in this problem we have entered the metal properties in the unit of watt per meter Kelvin. Then we have to create area in terms of meter. Further, so here it is a base plate. There is a rectangle. So for that rectangle, the base width is 5.25 centimeter and the height is 6.75 centimeter. In order to convert centimeter to meter, there is 5.25 divided by 100, 6 points for height, 6.75 divided by 100. Enter x1 distance 0, x2 distance 5.25 divided by 100. This is to convert from centimeter to meter. Then y1 distance 0, y2 distance 6.75 divided by 100. Again, this is to convert from centimeter to meter. And click apply. Here for the given dimension the base steel plate was created. Next, to create a insulator materials. To first create this insulator, the left side lower part, the width of the insulator is 2 centimeter and height of the insulator is 3 centimeter. Here 0.25 centimeters gap is provided at the bottom side and 0.25 centimeters gap is provided at the left side, and between the two insulators 0.25 gap is provided. So to create a first insulator, the x1 distance is 0.25 divided by 100 and x2 distance 2.25 divided by 100, y1 distance 0.25 divided by 100, y2 distance 3.25 divided by 100. Enter x1 distance 0.25 divided by 100, x2 2.25 divided by 100, y1 distance 0.25 divided by 100, y2 distance 3.25 divided by 100. Click apply. So here the first insulator is created. To create a second insulator, x1 and x2 distance are same, but y1 and y2 distance are changed. Y1 distance 3.5 divided by 100, y2 distance 6.5 divided by 100 and click apply. So here the second insulator material is created. To create this insulator, the total height is 6.75 and total width is 5.25. Here it is the starting point of this insulator. For that, the distance is 2.75 divided by 100, that is x1 distance. x2 distance 4.75 divided by 100. To calculate the height of this insulator, the total height is 6.7. Here the gap is 0.25 mm. Here the gap is 0.25 mm. And also the insulator height of the thing is 3 centimeter. So totally 3.5 centimeter. 6.75 minus 3.5. So therefore the 3.25 centimeter is for this top insulator and the bottom insulator. Then 3.25 divided by 2, that is 1.625 divided by 100. Enter x1 distance 2.7 divided by 100, x2 distance 4.75 divided by 100, y1 distance 0, y2 distance 1.625 divided by 100. Click apply. So here the insulator material is created. To create the center of insulator, 2.75 divided by 100, x2 distance 4.7 divided by 100, y1 distance 1.875 divided by 100 and y2 distance 4.875 divided by 100 and click apply. So here another insulator is created. Next one is to create a final insulator at here. For that x1 distance, that is 2.75 divided by 100, x2 distance 4.75 divided by 100, y1 distance 5.125 divided by 100 and y2 distance 6.75 divided by 100. Then click OK. Now we have successfully created a steel and insulator material. After creating a model, next is modeling, operate, boolean, overlap, areas, select the base area, then click OK. Select the base area and then further select the insulator materials and then click OK. So now it is overlapping, means one material is over the another one. Now close this, minimize this, minimize, minimize. After creating a model, next step is meshing, size control, manual size, lines, select all the lines, enter the element edge length as 0.001, click OK, minimize this. Next is go to mesh tool, select global set, select the element type as 1, material 1, click OK. Now select mesh, select the base plate and click OK to mesh with the steel plate alone. Next is to meshing of the insulator material. For that, click the raise hidden, go to element attribute set, select the material number 2, that is for insulator materials, click OK, select mesh, select the insulators and click OK to complete the mesh part. To confirm the different material properties, go to plot control, select numbering, select element or attribute number into material number, select the color only and click OK. Here are the two different materials are assigned for the given geometry. And minimize this and minimize the preprocessor. Next step is to apply a boundary condition. And then go to solution, analyze type, new analysis, steady state, click OK. Minimize the analyze type, define load, apply thermal, convection on lines, select the left side line, select the left side on of the steel plate, click OK, enter the flame coefficient value as 200 watt per meter Kelvin, enter the bulk temperature as 220 Kelvin, click OK, convection on lines, select the right side line, click OK, enter the flame coefficient value as 20 watt per meter Kelvin and enter the bulk temperature as 300 Kelvin, click OK, minimize this and next is solve current LS, close this and click OK. So here the solution is done. Close this. So next step is to get a result part. general processor, plot result, contour plot, nodal solution, select dwave solution, select nodal temperature, click OK. So here it is the maximum and minimum temperature for the given boundary condition. To save this file, go to plot control, select write meta file, select invert to white or black, select save as type as Windows meta file, enter the file name as dwave plot, save. To get the vector plot result, vector plot, predefined, select flux and gradient, select thermal flux and click OK to get a thermal vector plot. There is heat flux. To save this file, plot control, write meta file, invert to white or black, enter the file name as vector plot. Next one is to get a list result, general postprocessor, list result, nodal solution, select dwave solution, select nodal temperature and click OK to get the temperature at the various nodes. Here the maximum temperature is at the node number 166. The value is 252.21 Kelvin. Save this file, click File, Save As, enter the file name as dwave list and save. I hope in this video you know how to do the composite wall analysis for different materials. Kindly support this channel, like, share, comment and subscribe to get a further update. Thank you all.